Good morning, student. In the last period, we learned plane polarized light, optical activity, optical active compound, then dextrorotatory compound, levorotatory compound, chiral carbon atom, and optical isomers. Optical isomers are also known as enantiomers. The different form of the optical active compounds having the same molecular formula, same structural formula, but having a non-superimposable mirror image structures and having the opposite action on plane polarized light. That is, out of these two mirror image, one rotate plane polarized light towards right side, other isomer rotate plane polarized light towards left side. Then the optical isomers can be shown by which formula? Can be shown by features projection formula. That is, optical isomers may be represented by the Wedge formula as well as features projection formula. In Wedge formula, Wedge formula is represented on the plane of paper by representing the single bonds by using a solid wedge, dotted wedge, and the normal lines. This solid wedge represent the bond projecting up from the paper, that is towards reader, while the dotted wedge represent the bonds going backward below the paper, and the normal line represent the bond in the plane of paper. So, Wedge formula is represented by the solid wedge, dotted wedge, and the normal line. So, the Wedge formula of chlorobutane may be represented as in Wedge formula, the solid wedge represent the bond projecting up from the paper, that is towards reader, while the dotted wedge represent the bond going backward below the paper, and the normal line represent the bond in the plane of paper. That is, these two normal lines represent the bond, in the plane of paper, in the plane. Solid wedge represent the bond above the paper, while the dash wedge represent the bond below the paper. So, optical isomers can be shown by a Wedge formula. Similarly, The optical isomers can be represented by the features projection formula. Features projection formula. In features projection formula, the tetrahedral carbon atom is represented by a crossed line. Carbon atom is tetravalent. The tetravalent carbon atom is represented by a crossed line. The horizontal line represents the bond. The horizontal line represents the bonds projecting up from the carbon. That is coming out of the page. While vertical line represents the bond going into the page. That is going below the carbon atom. So, the features projection formula of the chlorobutane may be represented as the optical isomers may be represented, or optical isomers can be shown by the wedge formula as well as features projection formula. Then the next point is optical activity of compound. The optical activity of organic compound may be represented by the 3 points, may be represented by the following 3 points. For example, optical activity of 2-chlorobutane. Then we are going to explain the optical activity of 2-chlorobutane. Optical activity of 2-chlorobutane. As 2-chlorobutane contain chiral carbon atom. If the compound which contain chiral carbon atom, if the compound which contain asymmetric carbon atom, such compounds are optically active. It rotates plane polarized like towards right side or towards left side. So, optical activity of any optical active compound. Optical active compound, the compound which rotate the plane polarized like towards right side or towards clockwise direction, or the compound which rotate plane polarized like towards left side, that is towards anti-clockwise direction. Such compounds are called as optical active compounds. The optical activity of optical active compounds can be explained by the following 3 points. Number 1, presence of chiral carbon atom. Then point number 2, non-superimposable mirror image structures. And point number 3, racemic mixture. So, we are going towards the optical activity of 2-chlorobutane. 2-chlorobutane is structurally represented as according to IUPAC system, it is named as or alkyl halides are named as halogen. But the position of halogen atom is written before the name of halogen. Total number of carbon 4, therefore it is corresponding butane. It contains only one halogen atom. Halogen atom is present down a sheet. The position of halogen atom is indicated by the lowest possible number. That is, numbering is done from left side. That is, position of chlorine is 2. That is, chlorine atom is present on C2. So, according to IUPAC system, it is named as 2-chlorobutane. 2-chlorobutane is structurally represented as 2-chlorobutane contain only one chiral carbon atom. 2-chlorobutane contain only one asymmetric carbon atom. Chiral or asymmetric carbon. That is the carbon atom which is attached to 4 different atoms or 4 different groups. Such type of carbon atom is called as chiral carbon atom. That is the carbon atom which is attached to 4 different atoms or called as chiral carbon or asymmetric carbon atom. Such compounds are optically active. If the compound which contain at least one chiral carbon atom, it rotates plane polarized light towards right or left side. So presence of carbon atom, presence of chiral carbon atom or presence of asymmetric carbon atom, as compound contain at least one chiral atom or at least one asymmetric carbon atom, such compounds are optically active. 2-chlorobutane contain one chiral carbon atom, so it is optically active. It rotates plane polarized light towards right or left side. So presence of asymmetric carbon, presence of chiral carbon, it is one of the cause of optical activity. It contains one chiral carbon atom, so it is optically active compound. The presence of chiral carbon atom is one of the cause of optical active compounds. So, it is optically active. Point number 2, the optical activity of 2-chlorobutane or optical activity of any optical active compound can be represented by the following 3 ways. Can be explained by the following 3 points. Point number 2, non-super imposable mirror image structures. Mirror image structures. Point number 2, as 2-chlorobutane contain one chiral carbon atom, as 2-chlorobutane contain one asymmetric carbon atom, so it exhibits optical isomers. The number of optical isomers can be calculated by the formula A is equal to 2 raised to n, where A is number of optical isomers, N means number of chiral carbon atoms, number of asymmetric carbons, as 2-chlorobutane contain only one chiral carbon. Therefore, A is equal to 2 raised to n, A is equal to 2 raised to 1 is equal to 2. So, 2-chlorobutane contain 2 optical isomers. 2-chlorobutane contains 2 enantiomers. 2-chlorobutane contains 2 optical antipodes. These 2 optical isomers, these 2 enantiomers are the mirror image of each other. These 2 isomers, these 2 forms are the mirror image of each other, but having a non-superimposable mirror image structures and having opposite action on plane polarized light. These two isomers, these two optical isomers, these two enantiomers having the same molecular formula, having the same structural formula, but they are mirror image of each other and having the opposite action on plane polarized light. Out of these two isomers, one are rotated plane polarized light towards right side, that is towards clockwise direction. Such isomer is known as a dextro isomer. It is denoted by small d or plus sign. So one is D2 chlorobutane. Other optical isomer rotate plane polarized light towards left side, that is towards anti-clockwise direction. Such isomer is known as a Leo isomer. It is denoted by small l or minus sign, is named as L2 chlorobutane. So, in a second point, as 2-chlorobutane contain only one chiral carbon atom, it shows the two optical isomers. These two optical isomers having the same molecular formula, having the same structural formula, but having the non-superimposable mirror image structures and opposite action on plane polarized light. Now, third point, racemic mixture. Racemic mixture. It is denoted by small dm or plus minus sign. Racemic mixture. Actually, racemic mixture is optically inactive. Optically inactive, it does not rotate plane polarized light towards right side or towards left side. Racemic mixture contains equal quantity of dextro and leophor. That is a mixture which contains equimolar quantity of dextro and leophor. Out of these two isomers, dextro isomer rotate plane polarized light towards right side. Leo isomer rotate plane polarized light towards left side. That is in racemic mixture. The rotation of one isomer is cancelled by rotation of other isomer. Is called as external compensation. Due to external compensation, racemic mixture is optically inactive. External compensation, the rotation of one isomer is cancelled by rotation of another isomer. So, it exists in optical isomers. Out of these two, one is the dextro form, other is Leo form. As it contains equimolar quantity of dextro and Leo form, so it is optically inactive due to external compensation. As it contains equimolar quantity of dextro and Leo form, which is optically inactive due to external compensation, that is rotation of one isomer is cancelled by rotation of other isomer. Rotation of dextro isomer is cancelled by rotation of Leo isomer. So, or discuss the optical activity of any optical active compound. 3 points can be explained. Point number 1, presence of chiral carbon. Point number 2, non-superimposable mirror image structures. And point number 3, racemic mixture. So question may be, explain optical activity of the chlorobutane, or explain optical activity of lactic acid. Lactic acid is also optical active compound. It contains only one chiral carbon. It exists two optical isomers. So, as lactic acid contains one chiral carbon atom, one unsymmetric carbon atom, so it is optically active. It rotates like polarized light towards right or left side. Then next we are going towards the chemical properties of halogen. Chemical properties. Then we are going towards the chemical properties of halogen. Chemical properties. Number 1, laboratory test. Laboratory test or haloalkane. Laboratory test for haloalkane. Haloalkane. Haloalkane is the IUPAC name of alkyl halide. And alkyl halides are generally represented as Rx. That is, these are the monohalogen derivative of alkane. Monohalogen derivative of aliphatic saturated hydrocarbon. That is, compound is obtained by replacing one hydrogen atom of alkane by only one halogen atom. It is generally represented as Rx. Laboratory test for haloalkane. Haloalkane, IUPAC name of alkyl halide. Alkyl halide is common name of monohalogen derivative of alkane. So, in a laboratory test, alkyl halide or haloalkane is boiled with aqueous alkali. Aqueous alkali, that is aqueous NaOH or aqueous KOH. Both NaOH and KOH are the Arrhenius base. Both KOH and NaOH are the strong base. So, reaction of haloalkane with aqueous alkali. In alkyl halide, the carbon atom which is attached to halogen atom is electron deficient. Electron deficiency is due to electronegativity difference between C and X. In short, in alkyl halide, halogen atom is directly attached to sp3 hybridized carbon atom. But due to greater electronegativity difference between carbon and halogen, halogen atom is more electronegative. It contains, all halogen contains 7 electrons in their valence side, have a tendency to gain 1 electron for complete its octet. So, have a tendency to gain 1 electron. It is more electronegative. Electronegativity, tendency of an atom to attract electron towards itself. For complete its octet have a greater tendency to gain, to accept, to pulse electron towards itself. Due to greater electronegativity of halogen atom, both the electrons in a C electronegative halogen atom. As a result, carbon carries partial positive, halogen carries partial negative charge. This polarity is due to electronegativity difference between C and X. In short, in an alkyl halide, the carbon atom which is attached to halogen atom is electron deficient. Listen carefully. In alkyl halide, the carbon atom which is attached to halogen atom is electron deficient. So, which is then boiled with aqueous alkali. Aqueous alkali may be aqueous KOH or aqueous NaOH. In aqueous medium, it undergoes ionization to form K plus OH minus. In aqueous medium, it undergoes ionization to form a potassium ion and OH minus ion. OH minus ion is a strong nucleophile. K plus potassium ion is electrophile. OH minus is strong nucleophile. Nucleophiles are attracted towards electron deficient center. That is, haloalkane is boiled with aqueous alkali. The nucleophile, that is OH minus, is approaches towards electron deficient carbon atom. If it attack on electron deficient carbon, at the same time the fission of X linkage takes place heterolytically. Heterolytical bond fission takes place in presence of polar solvent. So, to form monohydric alcohol and halide ion. Haloalkane is boiled with aqueous alkali to form monohydric alcohol and halide ion. In this reaction, halogen atom of alkyl halide is replaced by the nucleophile, that is OH minus. OH minus is acts as a nucleophile. In this reaction, halogen atom of alkyl halide is replaced by nucleophile. Therefore, this reaction is known as a nucleophilic substitution reaction to form monohydric alcohol and halide ion. Then, the mixture is acidified. Then the mixture is acidified by adding dilute nitric acid and the silver nitrate. Then the white precipitate of silver halide is obtained. That is, Ag plus is reacts with halide ion. The oxidation state of silver may be +1. Is immediately reacts with halide ion to form white precipitate of silver halide. The mixture is acidified by mixing with dilute nitric acid and the silver nitrate. Then the white precipitate of silver halide is obtained, which indicate the white precipitate indicate the presence of a halogen atom in the original compound. The precipitate indicate the presence of halogen atom in the original compound. So we can detect the class of compound may be Then we are going towards SN reaction. SN reaction is named as a nucleophilic substitution reaction. An alkyl halide undergoes nucleophilic substitution reaction. An alkyl halide shows nucleophilic substitution reaction. In this reaction, halogen atom of alkyl halide is replaced by nucleophile. Consider the reaction when an alkyl halide is boiled with aqueous potassium hydroxide. In aqueous medium, potassium hydroxide undergoes ionization to form K plus plus OH minus ion. K plus is electrophile. These are the positively charged ions or electron deficient species, or neutral molecule containing electron deficient species attracted towards electron rich species. Nucleophile, these are the negatively charged ions or neutral molecule containing electron rich center and attracted towards electron deficient center. So, potassium hydroxide in aqueous medium undergoes ionization to form electrophile and nucleophile. In an alkyl halide, the carbon atom which is attached to halogen atom is electron deficient. The deficiency is due to greater electronegativity of halogen atom. Halogen have a tendency to gain one electron for complete its octet. So both the electrons are migrated towards more electronegative halogen. As a result, the carbon carrying the halogen atom in an alkyl halide, the carbon atom which is attached to halogen atom is electron deficient. So the nucleophile is approaches towards electron deficient carbon. If it attack on electron deficient carbon, but carbon atom is tetravalent, at the same time the fission of CX linkage takes place. The fission of CX bond takes place heterolytically. Heterolytic bond fission, any one of the partner retain both the shared electron. That is, halogen is eliminated in the form of halide ion. It immediately reacts with electrophile, that is K plus, and eliminate as a byproduct potassium halide. The product may be ROH, that is monohydric alcohol. Starting material, alkyl halide. In this reaction, alkyl halide may be converted into alcohol. In this reaction, halogen atom of alkyl halide is replaced by the nucleophile, that is OH minus. Therefore, this reaction is known as a nucleophilic substitution reaction. Alkyl halide undergoes NSR. Alkyl halide shows nucleophilic substitution reaction. Then SN reaction may be classified into two types. SN reactions, that is the depending upon the molecularity of reaction, the nucleophilic substitution reactions may be classified as SN1 and SN2 reaction. SN1, depending upon the molecularity. We know all reactants must pass through a transition state before they converted into product. The curve is obtained by plotting the rate of reaction or progress of reaction against potential energy. Consider the reaction A plus B gives C. Reactant species 2. A is reacts with B to gives product C. But reactant must pass through a transition state before they convert it into product. Transition state is high energy unstable state. In TS, molecule is unstable. Then the unstable molecule immediately loses, immediately converted into product. But all reactants, here A and B, both are the reactants, use product C. All reactants must pass through transition state before they convert it into product. The formation of TS is a slow state called as RDS. RDS means rate determining state. RDS, rate determining state, then the unstable transition state immediately converted into product. Molecularity, the number of reactant species taking part in the formation of TS. The number of reactant species taking part in RDS called as molecularity of reaction. If only one reactant species take part in the formation of TS called as unimolecular reaction, called as substitution nucleophilic unimolecular reaction. Out of these two reactants, only A take part in the formation of TS, then the reaction is substitution nucleophilic unimolecular. If two reactant species, both A and B, take part in the formation of TS, then the reaction is known as the substitution nucleophilic bimolecular reaction. So depending upon the molecularity of reaction, SN reactions are classified as SN1 and SN2. SN1, substitution nucleophilic unimolecular reaction. SN2, substitution nucleophilic bimolecular reaction. Then, next point, transition state. Transition state, it is high energy unstable state. If we plot the rate of reaction or progress of reaction against potential energy in a chemical reaction, all reactants must pass through a transition state before they convert it into product. Transition state in a TS, potential energy is maximum. It is high energy unstable state. It is high energy unstable state. All reactants must pass through a transition state before they convert it into product. Then the next point, energy of activation. It is denoted by delta E. It is the energy difference between TS and reactant, that is energy required to take reactant into transition state, is called as energy of activation. That is, it is energy difference between TS and reactant. Then delta H is known as the heat of reaction. That is energy difference between product and reactant. That is energy required to take reactant into product called as heat of reaction. Okay? झालं?